It's not just a conversation about how to get longer duration storage or more renewables or the path to net zero. It's also a conversation around industrial policy, right? How do we make sure that the dollars that are being paid by ultimately ratepayers is going to support domestic industries? That is, I think, what the U.S. IRA is focused on. I mean, this is a long, hard road. The only reason that we have lithium-ion batteries currently serving the electric grid is because Japanese electronics manufacturers in the 90s needed a very high-power way of getting their portable video cameras out into the market. In the 2000s, it was everyone started switching to laptops. Everyone decided they needed a smartphone. I mean, these were the developments that led to the maturity that we currently have in the lithium-ion battery industry. It's a very, very long road to get these technologies to the point where they are ready to make a meaningful dent in the electric grid. And I think if you look at the size of the batteries that we're building today, they're roughly equivalent, and we think we're treading the same path.
Hello, everybody, and welcome back for another installment of Transmission. In today's episode, Matt Harper, CCO at Invinity Energy Systems, joins our guest host Tim Overton to discuss Vanadium Flow batteries and where they fit in the storage lineup. If you're enjoying the podcast, please hit like and give us a rating. It really helps us reach a wider audience. Let's jump in.
Hello, everybody. Today, very exciting episode. We're joined by Matt Harper, who's the co-founder and CCO at Invinity. And quick disclaimer, I'm not Quentin Scrimshire. I'm standing in for Q. And so I'm Tim Overton. I'm the co-founder and CPO at Modo Energy. So be gentle with me and we'll see how this goes. But Matt, why? I've said kind of title and name, but maybe who are you? What makes Matt?
Who are any of us, Tim? I mean, let's think about it really. No, look, so yeah, you got it right. Matt Harper, CCO and co-founder with Invinity. My background is primarily engineering and technical. I trained as a mechanical engineer. I spent the first 10 years of my career in hydrogen and fuel cells. And then in 2005, went to work for a little company called VRB Power Systems that was the original licensee of a technology called Vanadium Flow batteries into North America. And essentially for the last, horrifying as it is to say, 18 years now, I've been pushing on, advancing the technology, advancing the products and commercializing those batteries and getting them out into the field.
Amazing. So, I mean, I might be completely wrong on this, but that seems like a very early entry into hydrogen. Hydrogen is a big word. Everyone talks about now. Fuel cells, it feels a little bit to me like they came and maybe went a little bit, but I feel like you were early in the game.
You're absolutely right. I sometimes joke that I started off on the ground floor in hydrogen, meaning I was, the intern lying on my back underneath a bus, bolting pieces of a fuel cell onto what was at the time the world's first fleet of hydrogen-powered vehicles. This is the fleet of 6 hydrogen buses that Ballard Power Systems, the company that I was with, had delivered into a couple of the North American transit systems, and it was very interesting and pioneering work. I mean, we've seen some evidence of where that has gone through to commercial applications today. But I think that the thing that became most important and interesting to me was less the mobility side of the world and more the grid and electric power side of the world, which is why I got interested in batteries and why I've been spending time there ever since.
That's very cool. And Vanadium Flow, it'd be great to have like a high-level explanation of what vanadium even is and what Vanadium Flow is. And then, yeah, I mean, we can dig into the details. Love it.
Yeah, that sounds great. So look, vanadium is a metal. It's the 13th most common metallic element in the Earth's crust. It's more common than copper, more common than nickel. The stuff is pretty widely available. What is not widely done, what is not widely part of its remit is it's not very widely used, right? Vanadium is used primarily in strengthening steel, and that's about it. So when we look around the world to see what vanadium does, there's a ton of the stuff lying around, but not a lot of it is actually processed into useful materials, which is one of the reasons why there's an opportunity to go and do something very useful with it, like make vanadium flow batteries. To touch a little bit about what that technology is and how it works, basically a flow battery takes the conventional battery technology. It's an anode and a cathode, but then it stores the energy inside the battery in a big tank of liquid rather than inside an individual packaged cell. What that means is that you can get to very, very large capacities in an individual battery cell. And you can extend the duration of storage, so the number of hours that you get out of a single cell at full power, out to a very long period of time. Certainly we focus a lot on 4-hour applications, but there's a lot of talk about what longer duration storage means, and that's an area where we can get out to sort of 6, 10, 12, 24 hours worth of storage comparatively easily, simply by increasing the amount of that vanadium liquid that's in the battery.
Okay, makes sense. And you say there's a lot of it. I guess, is it easy to get? That sometimes there's lots of things, but actually getting it to a useful form is not super straightforward.
Yep, no, it's a good point. It is. I think that most of the world's vanadium currently is generated as co-product from steel and iron ore refining and manufacturing. But and that's less useful for us because we want to have just the material by itself. The thing that's most exciting from our perspective in the vanadium space is that there are a large number of companies that are starting to refine the material from petrochemical wastes. There was a new low sulfur standard that came into offshore shipping fuels in the last decade. And that new standard has meant that oil refineries have to scrub sulfur out of those fuels before they go into the ships that sail around the world. Interestingly, one of the things that tends to come with sulfur out of those heavy crudes is vanadium. And so you've got these very large piles of what are otherwise waste lying around, refineries all around the world. That is a tremendous opportunity for us, not only to go and extract the material from what is ultimately a highly concentrated source of vanadium, but also making sure that we can get the material we need without having to go mining for new stuff and putting new holes in the earth, while also solving a waste problem at the same time.
Okay, sounds amazing. And then, so talk to me more about the kind of manufacturing. So we're getting the vanadium. It's a waste product, amazing, and anode cathode I kind of get, but the flow bit and I guess we're having to pump things around, and there's a lot more moving parts. How easy is it to actually get from?
Yeah, I would say I think the lots of moving parts is debatable. I was reading some quotes in an article from a head of battery systems development for an unnamed large multinational battery systems developer who said, quote, flow batteries are a maintenance nightmare because of all the moving parts. I would argue that if you look at most stacks of lithium-ion batteries, what you see is a huge amount of complexity in cooling, in balancing, and in taking those individual cells and actually turning them into something that isn't going to burst into flame every time you try and charge and discharge it by managing heat and by managing state of charge. Those are things that are much simpler for us to do in our battery. One of the great things about a flow battery, and especially vanadium flow battery, is that it's non-flammable. It's more likely to put out a fire than start one because it has that fundamental aqueous nature. Yeah. And so, some of the fact that the system itself, sure, it requires a pump to be able to circulate electrolyte, but we also rely on pumps for everything we do in our daily lives, and those things are pretty well evolved, they're pretty mature, and they're pretty reliable. Yeah. So that's definitely a difference between the technologies, but ultimately not something that we view as being a bit of a any form of challenge when we get these things out into the field.
And what does it look like? So I think people might be kind of familiar with seeing maybe now lithium ion solutions, either a big kind of 40-foot container or these kind of modular systems that are around. But yeah, are we looking at the same thing from the outside, or can you tell from miles away?
Yeah, no, you can't tell. It turns out that containers are a very efficient, low-cost way of moving stuff around the world. And if you can move stuff around the world in them, chances are they'll be sufficiently robust to protect whatever's inside them on a particular operating site for many years on end. One of the things that we do differently from every other flow battery manufacturer in the world is that we build every one of those modular units that go out into the field as standalone, totally turnkey flow battery devices. If you see, one of our 20-foot containers sitting on site, what you won't see is a whole bunch of extra components bolted onto the top of that thing. What you won't see is a whole lot of those tied together in order to do the work of the energy storage device. It's a totally modular, totally turnkey product that we are shipping out. We make sure that those batteries are fully functionally tested at our factory before they go out the door, and that means that our customers can know that they're going to receive something that works properly. We are going to have a data set that allows us to prove that the battery was working properly on day one, and benchmark the performance of those individual units before they leave our shop, and altogether that significantly decreases costs in terms of how to implement these technologies and the timelines upon which we can deliver, integrate, and get these batteries up and running.
Okay, yeah, makes sense. And in terms of, I'm not expecting you to give exact dollars on it, but like cost, are we talking cheaper, more expensive than, I guess, lithium ion?
Depends on how you want to measure it. The initial capital cost is somewhat higher. How much higher? Very much depends on what part of the market you're looking at. We're actually lower cost than a lot of lithium solutions for smaller scale projects. But if you benchmark our prices against the projects in the hundreds of megawatt hours that are being deployed, the very largest lithium battery projects that are being deployed around the world, yeah, we're somewhat more expensive than those very, very large installations. Now, with all of that said, we focus a lot not on the initial capital cost, but on the total cost of ownership of one of these projects over its lifetime. The fundamental benefit of a vanadium flow battery is that you get a very, very high throughput through the battery over its life, meaning that we don't see any degradation of performance based on cycle life. So you can get not a few hundred to a few thousand cycles out of these batteries, but you can get tens of thousands of cycles out of them. Not only can you get a lot of cycles out of them, but again, you're getting, remember that these are cycles that last for hours on end, full depth of discharge using 100% of the energy inside the battery. And finally, our batteries are designed from the ground up to be the right partners for renewable power plants. So designed as an asset that can last for decades alongside, wind or solar or other generating capacity that has that kind of durability associated. Now, what that high throughput nature means is that if you look at the total cost of delivering energy out of a battery over its life, and the metric that's usually used is the levelized cost of storage, we are significantly lower than lithium, even at any scale, because of the ability to pump more power out of these batteries over their operating life. And that, that may seem self-serving, like, wow, we've just tried to find a metric where it all makes sense. But if you look at other comparable industries as they've matured, solar being a great example, the LCOE of solar projects, or the total cost of ownership in some cases, depending on which side of the development fence you're looking on, very rapidly has become sort of the ultimate metric for figuring out what technology makes the most sense for application. There are some very, very high performance solar panels out there. There are some very, very low cost solar panels out there. But the technologies that optimize the two to get to that ultra low levelized cost of energy for solar are the ones that have won. And we think that is going to be the case with batteries as well.
Yeah, makes sense. And the thing that's interesting to me is, so it feels, to me at least, that Vanadium Flow is a new technology to come to market. But I guess this is something that you've been working on for, like you say, a while now. How have we cracked it? Is Vanadium Flow kind of ready for the world and the world ready for it? And what have you seen over the last 15 years? Are there still big changes happening, or is the technology kind of, we've made it?
Yeah, look, I think the technology is largely there. It's always a question of, that three-legged stool, technology, application, and markets. 10, 15 years ago, we'd walk into a boardroom and, try and talk about big batteries, and people would say, well, why? Who cares? I think that, with the amount of renewable generation that's being delivered onto the grid, and with the amount of instability in short-term markets and curtailment of overabundant renewable resources that we're seeing in a lot of jurisdictions, the fundamental, the philosophical case for storage is becoming very, very clear. As we go to a larger percentage of renewable power generation, breaking into the single, from the single into the double digits, even up to the 20 to 30% range, like what we're seeing in a lot of jurisdictions now, the case not just for storage but for longer duration storage starts to make a lot more sense. You're not just trying to use batteries to solve intermittency problems or power quality problems on the or capacity problems on the order of 5 minutes to an hour and a half. You're starting to ask questions like, can we take an overabundance of solar generation in an entire region and move it into the evening peaks where it's far more valuable? That's an ideal application for batteries like ours that not only can deliver 4 to 6 hours worth of full power all day, every day of the year, but do that in a way that they can do that work for the life of the generating assets that is generating that excess energy in the first place.
Yeah. Okay. And are we seeing, like, it feels like there's been a big push for energy storage in general, and like in the States with the Inflation Reduction Act, the IRA. Have you seen a step change in appetite for this kind of thing, or do you feel like it's been a gradual thing? And yeah, do you think more needs to be done to open up the space?
Yeah, look, to get back to that, the sort of the three parts of the stool that are ultimately going to support the work that technologies like this can do on the path to net zero. It's that regulatory piece that is still, I think, evolving, right? I often say to people that, people say, well, how have you not sold, 8 gigawatts of this thing so far? And there's an easy answer. The easy answer is that, markets don't lead technologies, right? Markets for appropriate solutions tend to be developed after those solutions become apparent. With vanadium flow batteries and with, high throughput, longer duration batteries in general, I think we are just at the stage of proving to the people who are designing markets, who are, implementing policy, who are crafting the interaction that these batteries will have in an economic manner with our energy system, are just finally realizing that the other two legs of the stool are already there, right? There is a need, there's a technology that can fill that need, and what is yet to be done is the work to figure out how that capability can be most appropriately compensated.
And are you seeing the kind of the same thing happening globally, or do you think the States and kind of GB, bits of Europe that are looking at storage, Australia? I mean, I've said a lot of places, but there. I mean, is this a trend everywhere? Yeah.
Yeah, look, it's happening in fits and starts all over the world. I mean, the UK, there are some very mature and I think well advanced markets for shorter duration storage, which is fantastic. It's not a perfect fit for us because it's focused on comparatively short duration capabilities. Certainly in Australia, what we've seen is a very significant recognition that it is that longer duration capability that's going to be needed. You look at states like South Australia, where they have negative prices for electricity on their spot markets, hundreds of days a year. I mean, this is a real challenge for getting more and more renewable generation on the grid, and they see that longer duration storage is something that could help make that happen. Certainly, the markets for electricity are one way that this kind of work can be compensated. The flip side of that are sort of direct incentives for the construction and operation and manufacturing of this class of product, this class of technology, and that's certainly where the Inflation Reduction Act in the U.S., the IRA, has focused. I think it's important to note that, I mean, this is not just a conversation about how to get longer duration storage or more renewables or the path to net zero. It's also a conversation around industrial policy, right? How do we make sure that the dollars that are being paid by ultimately ratepayers to get low cost, reliable electricity is going to support the domestic industries that have to go and basically deliver those goods. That is, I think, what the U.S. IRA is focused on, and I think that we've already seen other countries around the world start to adopt similar pieces of industrial policy, and I think that it has proven to be a good model for how we can advance the sort of the decarbonization and electrification goals of the future, while at the same time making sure that the work to make that happen is being done in a way that benefits the domestic economy.
Yeah. That makes sense. So this maybe sounds like I'm a bit of a slight, but it's really not. I'm just genuinely interested. Do you feel like people take Vanadium Flow seriously enough? I think I see there's some kind of technology that comes into the space that I feel like, whether it should be or not, it's grouped with like that will never really work. It's nobody really understands it, or like who's really going to build that technology. We hear kind of a lot of talk about hydrogen right now. There seems to be a lot of push for these kind of more generalized technologies. I don't think in general people hear about Vanadium Flow much. Do you think it's a problem, or?
I mean, define problem. I mean, look, I would love for my company and its products to have greater visibility. I also fundamentally believe that the products that we are building are solving one of the biggest problems on the route to net zero. So, even my own narrow self-interest aside, I would like to see more people adopting the kind of work that and products that we're doing. But I don't despair. I mean, this is a long, hard road, right? The only reason that we have lithium-ion batteries currently serving the electric grid is because Japanese electronics manufacturers in the 90s needed a very high power way of getting their portable video cameras out into market. These early development of portable devices, and then into the 2000s it was everyone started switching to laptops. Everyone decided they needed a smartphone. I mean, these were the developments that led to the maturity that we currently have in the lithium-ion battery industry. I mean, that's an industry that has essentially been very mature for a decade and a half, maybe 2 decades. It's a very, very long road to get these technologies to the point where they are ready to make a meaningful dent in the electric grid. And I think if you look at the size of the batteries that we're building today, with 75 megawatt hours out in the field versus the size of projects that were being delivered using lithium-ion batteries 5 or 7 years ago, they're roughly equivalent, and we think we're treading the same path.
Right, that's really cool. That 75 megawatts, that's Invinity's assets. Are there?
Yep.
Is there a large kind of number of other Vanadium Flow or similar assets?
Yeah, there's a number of companies around the world who are working to deploy the Vanadium Flow technology. Probably by the numbers, the biggest projects being delivered by others are being done by a number of players in China. There are a couple of projects that are pushing very close towards the gigawatt hour scale in China, and those are certainly the largest examples of Vanadium Flow being built today or being operated today. But yeah, I mean, look, we don't want to be the only company in this space, right? You start to look like the lone lunatic when you're the only one who's actually chasing after this point. But we've got competitors and colleagues in Europe and in North America, in Australia, and all over Asia who see the promise in this technology fundamentally and are working to get it deployed, and we're very happy to have them along for that ride.
Yeah, that makes sense. And for Invinity and you, I guess, is Vanadium Flow the that's what you're in and that's what you're staying in, or is there kind of a next step on the journey? Is there an upgrade? I don't know, a different metal or something kind of crazy that's on the roadmap?
No, there certainly could be. And if you look at, I mean, if you look at across the flow battery space in general, there are a number of different chemistries out there. There are iron flow batteries, there are organic flow batteries, there are zinc bromine batteries, which is more of a hybrid battery than a pure flow like what we build. But and they've all got different characteristics, right? If you want something that provides lower cycles but a lower overall cost, you can go one direction. If you want something that is good for cycling, not on the order of sort of hours to days, but in the orders of days to weeks, there are other electrolytes that are fundamentally lower cost that you can look to use to store that energy. I would say that there's a big conversation in the industry around what does longer duration storage mean? And some people say, well, it's 4 to 8 hours. Some people say, well, it's 8 to 24 hours. Some people say it's 24 hours out to months on end. Because if we're focused in that middle group, right? How do you deliver, say, 6 to 12 hours worth of energy on demand? And the reason we focus there is not only it's a good fit for our particular class of flow technology, but also if you look at sort of the jobs to be done by longer duration storage or by storage in general on the electric grid, really it's about firming renewables. And a lot of renewable power operates on a daily cycle. And this, solar is obvious, but even wind, especially in coastal areas, you get a lot of fluctuations in wind output that happens on a general daily basis. So being able to take, for example, 8 to 14 hours worth of good solar power generation and turn that into base load, that's an application that is where our batteries work very, very well, and where we see that solving that problem could just be an absolute massive leap forward for decarbonizing the grid.
Yeah, that makes sense. Do you see is most of your interest from private kind of funds, organizations looking to deploy and make a profit off these systems, or do you see a lot of interest from the kind of grids themselves? I guess they can also be private, but
Yep. No, we've seen a lot of interest from private operators, private developers. We've also seen a lot of interest from facility operators. We build our batteries for behind the meter applications as well, for electricity consumers who are looking to lower their electricity bills and often make better use of their own self-generated electricity if they've got solar panels on the roof, for example. But we announced about a month ago that we have been awarded 84 megawatt hours worth of business with the US DOE, and those projects are led by a number of utilities, regional utilities. So it is absolutely the utilities themselves are waking up to this problem of how do we make sure that we appropriately integrate renewable power, and they're making moves to make sure that they're going to be able to do so using technologies like ours.
yeah, okay, that's really cool. But it'd be interesting maybe to chat about one project in particular, maybe a recent project that you've worked on, and just give a picture maybe of how long it takes to build these projects, how big individual sites are, and kind of
Yep.
how they're scaling and how they're operating, whether you're happy with them.
Sure. Well, look, let me keep it close to home on this one. We just about 3 months ago brought online a project that we've built out in Alberta here in Canada. It's developed by a partner of ours, a company called Elemental Energy, who are a sort of mid-market developer and owner operator of both primarily wind and solar assets. How this project came to be is that Elemental had a site that they had control of where they were able to interconnect onto the electric grid, but the interconnection itself had a limited size. and they weren't sure that they were going to be able to get the right kind of returns out of it, given A, the limitations to how much throughput they could get through the interconnection with solar only, and B, the degree to which the peaks in market pricing on the electric grid in Alberta are at times when the sun isn't shining. Frankly, Alberta is cold. It's a winter peaking grid, unlike a lot of jurisdictions where we've got a summer peaking grid. People in Alberta need power to heat their homes, not cool their homes, like we see in Australia and California. And so it's so there was a hole in the ability of that project to be deployed profitably. Now, they had a 15 megawatt interconnection. What they ended up deciding to do was to take one of our batteries that has a peak capacity of about 3 megawatts, and then add basically oversize the solar site so that they've got 22 megawatts worth of PV generation capability now on that site, and a significant chunk of it is going to charge the battery. That combination of being able to generate more energy off of that site, while at the same time not changing the size of the interconnection, was the thing that changed the economics from their perspective and allowed them to greenlight the project and see it go forward.
How long did that project take from, like, I guess, greenfield or brownfield to an asset being operational? The Vanadium Flow bit, I guess.
About a year and a half. We had, Alberta is a tricky environment to build in. The ground is frozen for about 4 months of the year, so you've sort of got a no-go zone on construction from December through March. But yeah, ultimately it was about 18 months from the point at which we contracted with Elemental for the project, and alongside us, they finalized contracting for all the other components that were going to go into place. And when we went live with the system.
That's cool.
That's not atypical. We see certainly the fact that there was a grid interconnection already available and already on hand was helpful. We see around the world that those interconnections are becoming the bottleneck in getting these projects built and online. But otherwise, that 18-month development timeline from green light to operation is, I think, fairly standard.
Yeah. Are they noisy, Vanadium Flow batteries? Like, can you hear them running?
In fact, they're a lot quieter than. You can hear them running. Most of the noise that comes from them is related to cooling. We air cool the systems. We have little fans in there that blow air through the battery to keep it cool. But what we don't have are the sort of big refrigerant-based chiller systems that you typically see bolted onto the end of a lithium-ion container. So we are comparatively quiet, all things considered.
That makes sense. And I'm assuming the kind of downstream of the Vanadium Flow bit, the kind of system works and integrates in a very similar way to how you'd see how you'd see like lithium-ion systems plugging in.
Yeah, the one difference that we do on a significant majority of our projects, and certainly the project with Elemental is like this. The project that we are just putting the finishing touches on now in South Australia with Spencer Energy is this same way. We actually DC couple the batteries to the solar PV generation. What that means is that it's sort of a typical plant layout would be to combine both the batteries and the PV generation together on an AC bus, really at the call it at the fence at the plant fence at the boundary of that project. And by having those two, the generation source and the batteries coupled together on the DC side, it avoids having to do the conversion which imparts losses. You lose energy when you convert, say, the PV power over to AC and then back into DC to charge the battery. But the other thing that DC power configuration does, which is very helpful from a regulatory perspective, is it means that from the grid's perspective, you're only looking at a single inverter. and you can look at the rating on that inverter to set the interconnection capacity that's going on to a particular site. And then behind that inverter, you've got all sorts of additional ability to push and pull power as you see fit. You've got, for example, at Elemental, you can have a 15 megawatt inverter with 22 megawatts of solar and 3 megawatts of battery standing behind it, but never risk going over that 15 megawatt threshold. So in terms of the permitting and application process for some of these connections, that ability to DC couple is very, very helpful.
Yeah. Okay. And how many megawatts are going to be built over the next few years? Like, are we going to see gigawatt hours other than, I mean, you mentioned we've already got gigawatt hours in, I guess, China, but maybe kind of, more locally for you in the kind of States and your pipeline, how much Vanadium Flow are we getting?
Well, I can't, of course, provide forward-looking statements as a publicly traded company, but what I would say is that we have we have said publicly that we've got many gigawatt hours worth of capacity in our pipeline right now. I think the two forces that we see are the projects that we are building are becoming significantly larger. The number of projects where people are looking at the advantages of the technology that we're building and thinking, "Ooh, I could probably make some good use of that," is going way up. Certainly, factors like the IRA in the U.S. and some of the regulatory movements that we see in Australia and here in Canada are promoting people to look at this kind of technology a lot more comprehensively. So we do, we're very encouraged that that 75 megawatts that is currently contracted is going to start to look like a drop in the ocean sooner rather than later. The one thing that I would add to that is our current product was really designed for projects up to the sort of tens of megawatt hours. We have been working for the last few years with the team at Siemens Gamesa, the wind turbine company. It's interesting to note that solar and storage together has been sort of one of the biggest stories of the last 3 or 4 or 5 years in renewables in general. But you've heard very little about wind and storage together. Yeah. And there's two real reasons for that. One is that the scale of wind projects are so big that the batteries to support them would be far and away the largest batteries being built on the electric grid, even to take a dent in that wind turbine or wind farm output. And second of all, the duty cycle that you would need a battery to execute to be able to not only manage the intermittency that is injected onto the grid from a lot of wind sites, but also to manage the time of generation of the bulk of that electricity, making sure that wind that's blowing overnight is turning into electricity that people can use during the day. That's a big shift over the course of the 24-hour period that you need to make for wind energy to be more useful. That combination of those two things together means that regulating the output from wind turbines with lithium batteries is going to be very, very difficult because they wear out. And you would not have an asset that could stand alongside wind for the 20 to 30 years that wind turbines are intended to be in service. So the team at Siemens Gamesa reached out to us and said, look, we really like your technology. We think it is tremendously capable, not only in solving hours worth of energy shifting problems, but solving milliseconds worth of power quality problems. You guys can do both. And so we'd love to work with you to develop a product suitable for our fleet. The problem being that, again, it's that scale problem, right? We were building a product that was applicable in the tens of megawatt hours, and they needed a product that was suitable for the hundreds of megawatt hours to gigawatt hours and above. So we've been working with them on a joint development program for our next generation product, and we've already announced a few pioneering deals to deploy that product. The deal that I mentioned a few minutes ago to a handful of U.S. utilities will be some of the first examples of that next generation product delivered into North America. But because that product's fundamentals are designed for projects, like I say, in the hundreds of megawatt hours or above, we think that once that product is fully released and available to the market, we're going to see a very, very large uptick in the size of our install base.
Yeah. What are the challenges of going big? Because I mean, I'd imagined. So you've got loads of little tubes. What are the tubes made of? Are they metal and welded, or are they plastic and also welded, or how what is the challenge in going big? And I guess also what is the challenge in making them in general? I hadn't really thought about what the thing flows through.
Well, it's so what I mean, the tanks that hold the electrolyte they're big plastic tanks. They're like the sort of things that if you've got a farm somewhere, you might store 1,000 gallons of water in it. It's exactly the same kind of stuff.
Okay.
The conversion of that stored electrical energy, sort of stored chemical energy into electrical energy happens in a device called a cell stack, which is where more of the intellectual property is. It's where we spend a lot of our R&D dollars optimizing, and it's called a flow through cell. It's basically an electrochemical cell where you've got a positive and a negative liquid flowing through it.
Yep.
Ions pass across a membrane that separates the two, and that's where you get your electrical power. Those, the one of the things that we did when we founded the company that became Invinity about 10 years ago, as I mentioned earlier, I'd been in the space for about 8 years at that point, and we'd seen that there were a lot of very specialized materials that were being applied to make these flow batteries work, and we took the view that specialized materials that are manufactured at low volume were never going to be the right way to build an ultra low cost, highly durable product. And so we went and looked at what other industries were using for those materials. And for example, we found a carbon electrode that was being manufactured as blast furnace insulation. We found a membrane that was being manufactured not by the thousands of square meters for niche fuel cell applications, but by the tens of millions of square meters for water treatment. And so that approach of using readily available stuff to manufacture the core component of the battery with some of our intellectual property wrapped around it to make sure it actually does what we want was what we thought was a good approach, and we think that's borne out in the success that we've had in getting the cost of our product down to the point where it is competitive.
Yeah. Okay. And I guess it makes it easier to scale. Yeah, when you need to be doing these 100 megawatt hour projects. Very exciting. That's very cool. I think that Quentin normally does a plug in the podcast, but if there is anything that you want to plug, now's your chance.
Look, if I had to plug the product, what I would say is this is a technology that has been proven in the field. It is available now, and it is solving the next generation of problems in terms of how you integrate renewables onto the grid. Lithium-ion batteries have done a great job of proving that batteries in general can be a profitable and capable addition to the electric grid. But what we're building is the technologies and the solutions that are going to get us that next step towards a net zero future, where we're really using 100% renewable resources to serve not only the current needs on the electric grid, but also the incremental needs as we move towards decarbonization and electrification of home heating, of transportation, of all of those electrification steps that we all know we're going to need.
So, and I think the final thing is, what's your contrarian view? Like, what's your different view of the market?
Sure. Well, look, what I would say is that as much as I'm an engineer and a technologist, I think we have the technology we need to get most of the way, at least, towards net zero. What we don't have is the right investment, the right market structures, the right legal agreements, the right contract forms that are going to get us there. And I think that the challenge is that we're at a point where the technologies are fundamentally proven, but technologists don't necessarily understand finance and law, and the financiers and lawyers don't necessarily understand the technology. The work to be done is in pulling together those kind of multi-dimensional conversations. How can we take technologies that have been proven to do the work that needs to be done and deploy them in massive quantities. And that's why, I, as an engineer, sit on the commercial side of my company. And that's the work that I'm excited to do with all sorts of players in the market over the coming years and decades.
Amazing. Well, Matt, thank you so much for coming on. It's been an absolute pleasure learning about you and Vanadium Flow. Really cool.
Thanks, Tim. It's great to be here. It was great to be able to speak with you. And I would just say, for anyone who wants to learn more, you can find me either on LinkedIn or through our company website. That's invinity.com.